In this video, we're going to start drawing the mechanisms for some nucleophilic acyl substitutions, which we introduced in the previous video. In this video, the one common feature that will be in each of the exercises we do here, we will have is going to be a good leaving group. We're going to have an awesome leaving group, a chlorine. Each of these we're going to start with an acid halide, an acid chloride, and the chlorine is going to be our leaving group. That's a really good leaving group. These acid halides are the most reactive of any of the carboxylic acid derivatives. And so we're going to go up to D, exercise D, in this video. And in each of those cases, each of the molecules we'll be working with, the leaving group is going to be great. Not only that, but the carboxylic acid derivative that we're going to have is going to be really reactive. And the reason for that is because chlorine is very electronegative. Now, this carbonyl carbon is already slightly positive because the oxygen that it's double bonded to is stealing a whole bunch of electron density from it. In addition to that, though, chlorine is very electronegative, and that is stealing even more electron density. And so this carbonyl carbon is extremely electrophilic. It's a very vulnerable electrophile in this molecule. Not only that, but the chlorine is going to be a great leaving group. So this is very reactive, and we don't have to do anything to make it more reactive. It will react even with moderately strong nucleophiles. Like, you don't need the strongest nucleophiles to make this react. These acid chlorides are very reactive molecules. Notice the similarities between notice what happens overall in this reaction. Before we dive into what happens and how it happens, we have this carbonyl, a methyl group, and a cyclohexane ring on one side. Notice that that exact feature is there in the product. We have a carbonyl, a methyl group, and a cyclohexane ring on that one side. So that feature is exactly the same. What changes is the other group bonded to the carbonyl carbon. In the reactant, it's a chlorine. In the product, it is a nitrogen. It is an amine. Now notice, the amine is the exact molecule, the reagent that we're adding above the arrow. Now you'll see that that hydrogen there is not included in the product. And also, just to become more familiar with vocabulary, notice that what's happening here is we're taking an acid chloride, we're reacting it with an amine, a nitrogen with all single bonds around it, and we're getting an amide. That's a carbon double bonded oxygen with an amine on one side. Okay, but so that's in terms of vocabulary, but in terms of concepts, we have a nucleophile that's taking the place of a leaving group. So it's a substitution reaction. We see the carbon double bonded to oxygen, so this is going to be a nucleophilic acyl substitution. Okay, well, because we have an acid chloride, that electrophile, the carbonyl carbon, is already really reactive. So we don't have to activate it or make it more reactive than it already is. The nucleophile can simply attack it. The nucleophile that we have here, the nitrogen, in this six-membered ring with a hydrogen on it, that nitrogen has 3 bonds and 1 lone pair. Remember that nitrogen is in group 5a, so it has 1, 2, 3, 4, 5 valence electrons. It can form 3 bonds, and it always has that 1 lone pair, which allows it to act as a nucleophile or a base. Okay, so the lone pair on nitrogen, which is slightly negative, stealing electron density from the carbons and the hydrogen around it, that lone pair can attack the very electrophilic carbonyl carbon. The weakest bond breaks, and that's the pi bond. Those electrons go on to the most electronegative place nearby, which is the oxygen. And so if you're classifying this in terms of the curved arrow patterns that we've learned, this is nucleophilic attack, one of the necessary steps in any substitution reaction. Okay, once the nucleophile attacks, we get the famous tetrahedral intermediate. Notice that this carbon here, the carbonyl carbon, was sp2 hybridized and trigonal planar. But after the pi bond breaks, it becomes sp3 hybridized, and therefore tetrahedral. So this intermediate is going to be tetrahedral. The pi bond breaks, the electrons there go onto the oxygen on top, which now has a full negative charge. Let me write that in red. Moreover, the lone pairs on the nitrogen turn into a bond. So this nitrogen sort of moves up. And now we have a bond here. And this nitrogen, which has four bonds now, has a full positive charge. It had those electrons in the lone pair all to itself before. Now those are getting pulled away by this carbon in this bond, and so the nitrogen is losing electron density and has a full positive charge. In general, anytime nitrogen has 4 bonds, it has a positive charge. Okay, so this is our tetrahedral intermediate, and the oxygen up here with a full negative charge flailing in the wind is really unstable. Not only that, but the carbon that was the carbonyl carbon is extremely slightly positive. It's bonded to an oxygen, a chlorine, and a nitrogen. All of those are really electronegative elements that steal the electron density from the carbon. So the carbon is really electronegative, or really electrophilic. It's very slightly positive, and so these lone pairs that are unstable snap back to go toward that slightly positive charge. But in order to do that, this carbon already has 4 bonds. In order to form a new one, it would have to break one that's already there. And the most vulnerable one, the best leaving group, is the chlorine. So the chlorine gets kicked off the molecule, and if you were thinking in terms of curved arrow patterns, the curved arrow patterns we've learned, what is happening here, you would recognize this as loss of a leaving group. The other essential step in substitution reactions. So after that happens, the molecule we are left with, after the loss of that leaving group, the molecule we are left with first has a pi bond. This oxygen doesn't have a negative charge anymore. Those extra lone pairs become a pi bond. The chlorine leaves, takes its electrons, and departs. So that's our leaving group. And the amine now can serve as can sort of be written on the right side. Okay. Let me move the position of this hydrogen. It's still there. We have this hydrogen here, and that bond is going to that nitrogen there. So after the loss of the leaving group, this is what we have. Now it's almost our product. We just have this positive charge. The charges always, they're important to include because they always tell you whether something is stable or not. They tell you whether a proton transfer still needs to happen. Proton transfers change the stability or the reactivity of molecules. Now here we have a positive charge, and we can stabilize that positive charge by doing a proton transfer. We see an unstable molecule, we want to make it more stable. The way you can do that is a proton transfer. Now, we want to take an H+ off the molecule, so we want a molecule that will accept an H+. In other words, we want a base. And the best base that we have nearby is another amine. Remember that ammonia is the poster child. Ammonia, which is NH3, is the poster child for a Bronsted-Lowry base, because it has that lone pair that can attack a hydrogen and accept it. Well, in this amine that we have here, there is the same sort of feature. There's that lone pair. And so one of those amines can steal the slightly positive hydrogen here. Notice that that hydrogen is losing electron density to the nitrogen. The nitrogen is electronegative by itself. With a positive charge, it really tugs on the electrons in the bonds that it has. So the hydrogen is losing electron density, slightly positive. That makes this base attack it, and then those electrons snap back onto the nitrogen to help stabilize that positive charge. So we do a proton transfer to change the stability of this molecule. And when that's done, the hydrogen goes on to this other ring. So we have the nitrogen here and this other ring that we're not particularly interested in. This is a separate story, living its own story. And that has a full positive charge. That's a side note. That electrons in the bond go back onto this nitrogen, and that takes away the positive charge. So the final product you get is this whole molecule. Okay, let's go back. Notice that that is the exact molecule that we wanted. Okay, so overall what we accomplished is we replaced a leaving group, the chlorine, with a nucleophile, the amine. We turned an acid chloride into an amide, so an amide here. We did it by having a nucleophilic attack followed by loss of a leaving group. Those are the staples of substitution reactions. The nucleophilic attack is required to bring the new thing in that you're substituting the old thing with. Loss of a leaving group is necessary to replace the old thing that's there, so you can substitute it with another thing. And then the proton transfer we did in order to stabilize the molecule that we got. And I'll just point out one more time that we get this tetrahedral intermediate in between nucleophilic attack and loss of a leaving group. Okay, let's see how that plays out in our next reaction in B. Here again, we have an awesome leaving group, chlorine. The chlorine is not just a good leaving group, it's also really electronegative, so it adds to the effect of the oxygen and makes the carbonyl carbon here really positive. So this is slightly negative, the chlorine is slightly negative, and this carbonyl carbon is really electrophilic. So this is very reactive. It will even react with weak nucleophiles, and that's what we have here, methanol. Remember, the Me means CH3, so another way of drawing this is just like that, where this is a CH3. Okay, so what's going to happen? Well, if we look at the overall structure, notice that the carbonyl and the benzene ring is present in the product, carbonyl and benzene ring. All that changes is the chlorine, the leaving group, switches places with the nucleophile. Now you'll notice that this hydrogen in methanol is not still there, so we're going to have to do a proton transfer to remove that. But otherwise, this is a nucleophilic acyl substitution. You're substituting chlorine with a methoxy group, and those are connected to an acyl group, a carbon chain that has a carbonyl on it. Okay, so we can take our molecule, benzene ring, connected to our acid chloride. The carbonyl carbon here is really electrophilic, so even the methanol, which does not have a full charge and so is not a very strong nucleophile, even that, the slightly negative charge on that oxygen, is strong enough to allow the methoxy group, the methanol molecule, to attack the carbonyl carbon. Now once that attacks, that carbon already has 4 bonds, the weakest bond has to break, and as we discussed in the previous video, that weakest bond is the pi bond. So the pi bond breaks and the electrons go up onto that, the most electronegative place nearby, which is the oxygen. Now if you were going to classify this in one of our 4 curved arrow patterns, this would be nucleophilic attack, one of those necessary steps in any substitution reaction. Okay, so the product you get after that forms is the famous tetrahedral intermediate. So this pi bond won't be there anymore. It'll wind up as a 3rd lone pair on that oxygen, which now has a full negative charge. And this lone pair will turn into a bond to the methanol. That oxygen now has 3 bonds and therefore has a full positive charge. Okay. So that's our molecule. That is our tetrahedral intermediate. Notice that the carbon that was sp2 hybridized is now sp3 hybridized, and therefore tetrahedral. Well, this molecule is not stable. You can see the charges on it that are all pointing to the fact that it is an unstable molecule. And so the first thing, and the least stable thing, is this negative oxygen here. It's flailing in the wind with its full negative charge, and tauntingly, right next door, there's a partial positive charge on that carbon. Because notice, it's bonded to 3 very electronegative elements, the oxygen, the chlorine, the other oxygen. So it's losing electron density to all 3 of those atoms, and is very slightly positive. Well, that's very attractive to this oxygen with the full negative charge, and one of the lone pairs swoops down to try to form a new bond there. But if it does, that carbon already has 4 bonds. It has to break one of the bonds to one of the things already on it. And the best leaving group here is the chlorine. So the chlorine acts as a leaving group. It pops off of the molecule. And so if you're going to classify this curved arrow pattern in one of our 4 curved arrow patterns, this would be loss of a leaving group. Another necessary step in any substitution reaction. So here, what we end up with after this is the chlorine leaves. So that winds up, it takes its electrons, it leaves, and it winds up with a full negative charge bouncing around the solution. The oxygen uses its lone pair to form another pi bond, and that relieves it of negative charge because it's sharing those electrons now. And I'm just going to position this methanol molecule so that it's sort of to the side. Technically, this molecule is already our product, but I'm going to make that bond go a little bit to the side just so to make it look more conventional. Okay, so that is our molecule so far. Now, we'd almost be done, but the charge is pointing out to us that this molecule is not yet completely stable. So we're going to have to do a proton transfer to stabilize the charge there. And we would have seen this coming. You might remember from Organic Chemistry 1 that if you ever use a nucleophile that's neutral, after it adds to the molecule, it has a positive charge, and you have to do a proton transfer to stabilize that. You might remember that from the complex mechanisms for SN1 reactions. So another methanol can come by, and the slightly negative oxygen can steal this slightly positive hydrogen here. This hydrogen is losing electron density to the oxygen. First, because the oxygen is electronegative, and second, because it has a positive charge, so it's really stealing electrons away. So when the other methanol molecule snatches it off, these electrons in this bond snap back onto the most electronegative place nearby, which is the oxygen. And we end up forming, and this is an equilibrium reaction. We end up forming this methanol with a positive charge on the oxygen and this here. Now I'm going to reposition this methyl group. Oops. And so that is our product. That is actually the product we want. And when we look back at the way they have it drawn there, above, it will look like this. But remember that Me is a methyl group, which is what we have right there. So that is our product. That is what we wanted to get. When you look at this here, that's what we have there. And the overall transformation we have is just a nucleophilic acyl substitution. We replaced a leaving group on an acyl group, a leaving group on a carbonyl, with a nucleophile that came in. We had to do nucleophilic attack. That gave us our tetrahedral intermediate, which snaps back down to give us loss of a leaving group. And then we just did a proton transfer. That's what this curved pattern is in this last step, proton transfer, to change the stability of a molecule. In this case, we wanted our product to be more stable. It had a positive charge, so we removed an H+, and that gave the final molecule a 0 charge and made it more stable. And that is our nucleophilic acyl substitution for this reaction. We took an acid chloride, we treated it with an alcohol, and we got an ester. Okay, so let's think about C. It's going to be a similar thing. If you look at what's similar and what's different in this molecule, you have a carbonyl with 2 oxygens on one side. And you'll notice you still have that in the product, carbonyl with 2 oxygens on one side. What's different is the other group added to the carbonyl. In the reagent, it's a chlorine, which we would recognize as a good leaving group, and in the product, it is a sort of acetate group, or propanoate group. And we would see that the functional group we have there on the right is an anhydride, an acid anhydride. Well, that looks very similar, or I should put that in red, that looks very similar to the nucleophile that we're adding above the arrow. So again, we can recognize this as a nucleophilic acyl substitution. We have the acyl group, and we're going to use a nucleophile to replace a leaving group with itself, so to substitute itself for a leaving group. Okay, well, we have this acyl chloride, this acid chloride. And the carbonyl carbon, as we've seen with this, acid chlorides are the most reactive of any of the carboxylic acid derivatives because the carbonyl carbon is extremely slightly positive. The oxygen is pulling electrons away from it, the chlorine is pulling electrons away from it, so that carbonyl carbon is very electrophilic. So we can take our nucleophile, which here is this propanoate molecule, which has a full negative charge. And that nucleophile can attack our electrophile. So these lone pairs sweep up, smack that carbonyl carbon, and then the weakest bond breaks, that's the pi bond. Those electrons snap onto the most electronegative place nearby, which is the oxygen. So that oxygen, which had 2 lone pairs, will now have 3. Now if you're going to classify what's happening here in terms of our 4 curved arrow patterns, this is nucleophilic attack. Okay, so after that nucleophile attacks, we're going to get our famous tetrahedral intermediate. So the pi bond will break. That becomes a new lone pair on this oxygen, which now has 3 lone pairs and is therefore fully negative, has a full negative charge. The other lone pair on this acid halide, and actually, let me rotate this a little bit, that is going to form a bond. So one of these lone pairs ends up forming a bond after it attacks as a nucleophile. And that's our intermediate, our tetrahedral intermediate. You'll notice that this carbon, the carbonyl carbon, was sp2 hybridized and trigonal planar, flat. After the nucleophile attacks, the pi bond breaks, and so it becomes sp3 hybridized and now is tetrahedral. So we have that tetrahedral intermediate. The other thing you should notice in this intermediate is that the oxygen has a full negative charge and is very unstable. Not only that, but the carbon next door to it is very slightly positive because it's bonded to 3 electronegative atoms. The oxygen on top, the chlorine to the right, the oxygen on the bottom. All of those atoms are stealing electron density from that carbon, so it's very attractive to the negative oxygen, and their instabilities complement. The negative oxygen, the electrons on there, swoop down to form another pi bond. That carbon, however, already has 4 bonds, so if it's going to form one of the ones it has to break. And the best leaving group here is the chlorine, so that pops off the molecule. And that, overall, if you had to classify that in one of our 4 curved arrow patterns, would be loss of a leaving group. Loss of a leaving group. Okay, so the tetrahedral intermediate collapses, and what we're going to get after that collapse is the chlorine will leave. Oops. So the chlorine leaves. The electrons here form a new pi bond. And this technically is the product, but it looks really weird. So I'm going to move this bond over just a little bit so it reflects the actual bond angles a little bit better. And you have that as your product. And somewhere floating around in the solution is a chlorine. Now notice that we don't have to do a final proton transfer here. And that should make sense because our nucleophile was not neutral. It had a negative charge to begin with. You only have to do a proton transfer after nucleophilic attack if the nucleophile that you use has no charge to begin with. Because then when it reacts, it develops a charge and you have to stabilize that with a proton transfer. But if it starts with a full negative charge, then when it attacks, that charge goes away and it's just neutral. So notice that the product we want is the product that we just drew down here. So you have just the two staples in this reaction. You have nucleophilic attack to give a tetrahedral intermediate, which then crumbles apart, giving you loss of a leaving group, so that a leaving group is replaced by a nucleophile. So it's nucleophilic acyl substitution. Okay, one last one for this video. And here again we have an acid chloride, very reactive molecule. If we're trying to see the differences in here, what changes overall, we have a carbonyl and then a sort of isopropyl group next to it. So a carbonyl and a sort of isopropyl group next to it. The chlorine we recognize as a leaving group. The nitrogen in ammonia, the nitrogen equivalent of water, is a nucleophile. And we see that that replaces the chlorine on the molecule. So this is going to be a substitution reaction. A substitution reaction caused by a nucleophile, so a nucleophilic substitution reaction, on a carbon chain that has a carbonyl. So a nucleophilic acyl substitution reaction. Okay, well, how would this happen? We have our acid chloride to begin with. And the carbonyl carbon here is extremely electrophilic. It's very slightly positive. It's losing electron density to the oxygen above it and to the chlorine to the right. So that makes it very slightly positive and very vulnerable electrophile. And so, if a nucleophile like ammonia, the nitrogen equivalent of water, if ammonia comes in, and that nitrogen has a slightly negative charge, it can attack the carbonyl carbon already, because it's already really reactive, and the weakest bond, the pi bond, will break. The electrons will go to the most electronegative place nearby. That's the oxygen. So if we're going to summarize that curved arrow pattern, if we're going to summarize what happens there in one of our 4 curved arrow patterns, you'd recognize that as a nucleophilic attack. Nucleophilic attack. A necessary step in any substitution reaction. Okay, well that nucleophilic attack is going to give us our famous tetrahedral intermediate. So first of all, the pi bond will break, the electrons will go onto the oxygen to give that a full negative charge. So that's really unstable. And then this ammonia is going to bond. Now it won't have that lone pair anymore. That lone pair is going to be used to form a bond to the nitrogen. Notice that the carbon that was trigonal planar, because it was sp2 hybridized with the pi bond there, the carbonyl carbon, is now tetrahedral. It only has single sigma bonds. So it can combine all of its p orbitals with its s orbital, sp3 hybridized, and so tetrahedral. So we have our tetrahedral intermediate. The very unstable oxygen there is swinging around, flapping in the wind, and the carbon next to it is very slightly positive. It's losing electron density to the oxygen, the chlorine, and the nitrogen. So it's very slightly positive. It's attracting these lone pairs on this oxygen, and so those lone pairs snap back down and try to form a bond to it. Now the carbon already has 4 bonds, so if it's going to form a new bond, it has to kick one of the things on it off. We have a very good leaving group, the chlorine. So the chlorine pops off the molecule, and if you had to classify this according to one of our 4 curved arrow patterns, this would be loss of a leaving group. So after this step, what you'd end up getting is the chlorine, which would come off, the chlorine would separate, have a full negative charge, and be floating around somewhere else in the solution. The oxygen, that lone pair there, will turn into a bond. And then, this is technically our product. We just want to draw this ammonia in a slightly more conventional way that reflects the bond angles, the actual bond angles a little better. So I'm going to move that around just a little bit. Okay, now that nitrogen has 4 bonds, and therefore it has a full positive charge. And that's a sign that we just need to do a proton transfer to stabilize it. So if we remove an H+, then that will lose the positive charge and become more stable. So you change the reactivity of molecules by doing proton transfers. Now we have ammonia in the reaction solution, and ammonia is famously a Bronsted-Lowry base. Ever since General Chemistry 1, you would want to recognize that as a Bronsted-Lowry base. The lone pair on top, and the nitrogen is slightly negative, and the lone pair on top is open to the world, so we can easily steal one of these slightly positive hydrogens, and actually, let me steal this one, and the electrons can snap back onto the most electronegative place nearby, which would be that nitrogen. So after that proton transfer, you'll have a very clear, stable molecule. So that molecule there. In addition to that, you'll have ammonium. Now ammonia is just nitrogen with 3 H's. If you bond it to 4 H's, so the conjugate acid of ammonia, it has a full positive charge, and that is ammonium. That has its own story. Here we're concerned with the story of the carbon molecule. And you'll notice this is the final product that we wanted to explain in the beginning. So here, that's what that was. Okay, well, if we're trying to use vocabulary, we could say we took an acid chloride, we treated it with ammonia, and we made an amide. Ammonia is very easy to get. It's basically a whole bunch of cleaning products, and you could buy it all by itself. Now we did that nucleophilic acyl substitution first by doing nucleophilic attack. That gave us our famous tetrahedral intermediate. The negative oxygen in that snaps back down to produce the loss of the leaving group. And then we just needed to stabilize the nucleophile by doing a proton transfer. And there was a hint that we'd have to do that because our nucleophile did not have a full negative charge when it was by itself. So after it forms a new bond, it will create a positive charge, and we had to do a proton transfer to stabilize that. And that gives us our final product. So in this video, we've talked about how you can show the mechanism for nucleophilic acyl substitution reactions that have really good electrophiles. In every single example in this video, we've started with an acid chloride, which is a really good electrophile. And so we didn't have to do a proton transfer to make that more reactive. Well, starting in the next video, we're going to start using carbonyls, carboxylic acid derivatives, that are not as reactive, so esters and amides. And because those aren't as reactive, we're going to have to do more proton transfers to change their reactivity to make the reaction happen. So you can sort of think of these as a standard nucleophilic acyl substitution reactions, and the ones we're going to do in the next one's also standard but slightly more complex because the carboxylic acid derivative we'll be dealing with will not be as electrophilic.